Hello. We were continuing our discussion about gas and gas laws. Just going to take a trip down memory lane. So remember we talked about P1 V1 equals P2 V2, right? And that was an example of Boyle's law. Let's put a B for Boyle. Then we had V1 over T1 equals V2 over T2, and that would be Charles's law. All right, and then we had P1 over T1 equals P2 over T2. We've got the 1, and that would be Lusak's law. Okay, so now these are all contingent on the fact that things that are constant. All right, that's my short abbreviation for constant. Well, in all three, the number of particles are constant. Okay, so in Boyle's law, well, what's the thing that's not constant other than the particles? Well, if you notice, it's pressure times volume. All right, so that means temperature is the thing that we need to hold constant. Okay, and for Charles's law, all right, you can see that we're dealing with volume and temperature, so those obviously can't be held constant, so pressure has to be held constant. And if you figured out where this is going in Lusak's law, we're talking about pressure and temperature, so that means volume has to be held constant. All right, so these were the three gas laws that we discussed, and we went over problems with those gas laws. Now, it's very difficult to keep temperature, pressure, and volume constant. You can do it, but it's challenging, and you have to, have really strict parameters for those experiments that you're doing. Now, what we're going to look at is, well, what happens when we keep the particles constant, but when temperature, pressure, and volume are not constant? How can we use these laws? Well, a long time ago, someone realized that if you multiply all these laws together, you don't have to keep pressure, volume, or temperature constant. All right, but the number of particles must be. Now, we'll get to what happens when the number of particles changes the next time we talk about the ideal gas law. So, for right now, we're going to talk about something called the combination gas law. All right, the combination gas law is a gas law when you take these three gas laws and you multiply them together, and you don't have to worry about temperature, pressure, or volume being constant as long as the number of moles are the same. And that's pretty simple as long as the container is closed. Usually we do these things in something like a movable piston. All right, so again, if this is a cylinder, okay, you usually have the piston head, like in an automobile, connected to something, and this can move up and down, or something like a balloon, or the container could be changed. All right, so that's what happens when volume is changing. So let's see how this combination gas law that we're talking about is derived. Okay, so all right, it's really simple to do. All we have to do is take P1 V1 equals P2 V2, all right, which is Boyle's law, and then we're going to multiply it by, I don't know, it doesn't make a difference because it's a distributive property, so we'll multiply it by Charles's law first, okay, and that says that this side would be V2 times T2, and this would be V1 times T1. All right, distributing that out, we would get P1 over V1 squared over T1 equals P2 over V2 squared times T2. All right, sorry, a piece of my my pineapple on there. Anyway, so let's multiply it now by Lusak's law, which is P2, T2, P1, T1. Okay, we get P1 squared times V1 squared. That does not change, so T1 squared equals P2 squared times V2 squared over T2. Well, that's a pretty, looks like a headache there with all the squares. Now, one way we can simplify this is to take the square root of both sides. And we get P1 times V1 over T1 equals P2 times V2 over T2. So in any textbook you look at, if you look up combination, because again this is called combination gas law. Any textbook you look in, you'll find that. I find that students have a little bit of tough time with this, so I just multiply both sides by T1, and in that case, if we multiply both sides by T1, it cancels out over here, and then I want to bring T2 upstairs, so I multiply T2 on both sides, right, and we get more of a linear equation. All right, cleaning this up a little bit. We get clean sheet of paper. I guess I could write on this one. Again, P1 V1 times T2 equals P2 V2 times T1. Okay, so what would a typical combination gas law problem look like? Okay, so here we go. So I'll read this out for you. So we have a student maybe new to chemistry. Hannah has gas with a pressure of 15 atms. Again, atms is a pressure of, a unit of pressure, and a volume of 4.800 liters, and a temperature of 29.65 degrees Celsius. The gas is in a movable piston with a constant number of particles. Okay. The volume in the piston was reduced to 1.575 liters, and its pressure was increased to 32 atms. What is the Kelvin temperature under the new conditions? So I'll see if you can figure this out. I'll give you a couple minutes. Hit pause, and we'll be back at it, and we'll see if you got it right. Okay. Okay, so hopefully you came up with the right answer. All right, let's go back to our equation. What I tell people to do is to create yourself a nice data table. All right, and these problems are kind of wordy because this is a 6-variable problem. You have to be given at least 5 of the variables, all right, or at least have one of these constant, all right. But that really wouldn't be too an interesting combination gas law problem if the pressure or volume or temperature was held constant. So let's see, what do we know? So let's write down P1, V1. Now, you don't have to do this. Since T2 is on this side right here, I like to write T2 with P1 and V1. then we go P2, V2, and then eventually T1, again, because it's on this side of the equation. You don't have to do it this way. I just find that it's easier. Okay, so with that being said, all right, we have a pressure of 15 atmospheres, volume of 4.800 liters. T2 is the thing we're going to be solving for. Again, this is in Kelvin. All gas law problems should be done in Kelvin. We said that the pressure was increased to 32 atm, and the volume was decreased to 5.75 liters, and the new temperature was 29.65. Again, putting that into Kelvin, we'll add to 73.15. Again, two places behind the decimal because it should come out to 308. 302.80 is your new Kelvin temperature. I know there's an 8 in there somewhere. All right, let me put that back up. So that's a 2 right there. Anyway, so now we can plug into the equation. All right. I'm going to skip all the units here because we're going to be dividing and they'll cancel out. If you really want to rearrange the equation to solve for T2, then it would be T2 equals P2 over V2 times T1 divided by P1 over V1. All right, and then you could just plug in P2, again 32 atmospheres. You know what, I'll just write the units in there. All right, V2 1.7575 liters. Okay, and T1 we said is 302.8 Kelvin. All right, divided by the initial pressure. Again, we're looking for T2. The initial pressure was what, 15 atmosphere. The initial volume was 4.800 liters. All right, so atmospheres goes bye-bye, liters goes bye-bye. And we want to solve for T2, and if you did this correctly, now again, when you are dividing these two numbers, make sure that you multiply these two numbers first, all right, or make sure they're in parentheses in your calculator. Okay, so what I got for T2, hopefully you got the same thing, is 211.96 Kelvin. All right, and that is the combination gas law. Okay, again, if you have any questions, you may email me anytime, and I will get back to you as soon as I can. All right, the next video should be coming soon, and that's about the ideal gas law. That's when the number of particles will start to change. Okay, goodbye for now.